So before we get started, just a reminder that the first test is this coming Friday. Hopefully it's not a surprise that I say that. Basically, will be over everything we've done so far with integration and accumulation, up to and including volume so far. He might actually introduce introduce one more concept tomorrow, but so any questions about the test this Friday or what it's going to cover, anything at all?
Will there be any of those questions that, the conceptual questions, the ones that like help us build the problem? Like
yeah,
the worksheet?
You should definitely be ready for that kind of treatment. So, yeah, so much of what you're expected to understand and the ways you're expected to know these concepts is, has more to do with getting to the answer than the answer itself. So yeah, be prepared to discuss like how you build these things up rather than just how you finish
them. Is the test going to be on Lockdown browser or is it going to be through something else?
I am pretty certain it's going to be through Lockdown browser. So what happened last semester, and I wouldn't expect this semester to be much different, is that it was handled on Lockdown browser. I think he gave like a 2-hour window for when you could start the exam. And then you had, I think, 90 minutes to complete it once you started it. Rodolfo asked, will there be word questions like the quizzes? Yeah, absolutely. Yeah, so, and one thing I will say that, if you haven't already seen it, if you haven't already been there, if you go to Canvas, there's a module entitled exam prep or test prep, something to that effect, but there should be a couple of pages in there now, and it links to a couple of worksheets that are really good review. So, and hopefully it's not too much of a surprise for me to say this, but yes, you should be able to make the calculations, but it's more important to be able to know how you arrive at the calculations you need to make.
Last question for me about the test. Are we allowed to have like our notes, or is that like one note card? I know some teachers don't only do an index card.
No, so yeah, it's just you and your calculator basically. So
most notes?
No notes.
Okay, thank you.
And I think yeah, last semester what you were required to do before you started the exam is basically do use your camera to take a picture of your work area.
Oh goodness, my work area is a giant mess.
Everyone's is. So long as that mess doesn't include like an open math textbook or a bunch of notes. We're not trying to judge your cleanliness, just your honesty.
I had a question. Since it's going to be on Lockdown browser, we won't have access to like the GC calculator, which will
in fact,
have.
Yeah, and that's a good question. The test is written in such a way that you don't need GC.
Okay, but like, do we still need to like know basic, like, or not basic, but like Calc 1 differentiations and integrations for like certain things?
So while I don't want to promise you what's on the test, because I don't know, I have not seen the test, but keep in mind the kinds of things you've had to do so far. And what that doesn't include is, computing derivatives by hand or computing integrals by hand. It's been a lot more focused on, for example, when we've found signed area, unsigned area, volume, all those things. Once we figure out what the integral looks like, you have not been calculating them by hand.
Now, what about like using like like a regular calculator? Can we use that or no?
As far as I know, and I believe last semester he allowed the use of calculators.
Okay.
But again, I don't know if he's made that decision this semester yet. I'm sure he will talk to you about it tomorrow, but keep in mind how much we are able to do without using a calculator at all. In fact, I think everything I'm going to do with you all today is all very much calculus, but I don't think any of you will need a calculator. Gabriella asks, since we do not have GC, there will be graphs presented to us, right? Well, keep in mind that he has given this advice, and I have tried to echo it, that when you're trying to deal with area and volume, if I give you a function, you should be able to sketch, not a terribly accurate one, that's not super important, but you should be able to sketch a graph to just help you organize yourself. So do not assume that you'll be given a graph for a function that you'll be needed to do some work with. Anybody else? All right, I'm gonna go ahead and get started. So I'm gonna share my screen. If you don't have it handy already, have a paper, pencil, iPad, whatever you use to take notes with. Basically, we're gonna focus all day today on volume accumulation. And I am not sharing my screen, am I? I'll need to do that first. All right. So I have this trapezoidal region down below on this equi plane. So I'm going to give you a few minutes to work on these three things. So I want you to, draw the empty shell you create with this region when you revolve it around its left end, its top edge, and its bottom edge. So doing those three things should give you three distinct solids. Go ahead and spend the next few minutes working on those, and then I'll show you what my sketches look like in just a bit.
Is it revolving horizontally or vertically? Guessing horizontal.
That should be basically you're using whichever edge as the axis of rotation.
Okay.
So that alone should tell you if you're doing horizontal or vertical. All right, let's go ahead and take a look. I'm gonna go ahead and stop sharing here and share from my iPad instead. All right. So So the first one I want to do is revolving this thing around the left-hand edge. So first I'm going to just highlight the edge, that basically this right here, and I'll extend it out infinitely. This is essentially our axis of rotation. So the left-hand side of this shape, we're going to revolve. So basically we're going to take this area that I'm shading in, and we're going to revolve it around that vertical line. So the first thing I'm going to do, and I mean, if you all have some way that works for you that kind of helps you visualize this process, that's great. I'm going to show you what I do. Hope maybe it'll be helpful to some of you. So the first thing I'm going to do is I'm going to stay in 2 dimensions and just reflect this over the over that vertical line. So from there, we know we're going to revolve this thing around this axis. So that's going to give rise to this, you know, circular bottom, circular top, which is kind of hard to represent in 3D, but like I said, this does not have to be accurate or beautiful. It just kind of has to help you organize what you're going to be doing. So you end up getting like this, you know, Reese's peanut butter cup shape looking thing. Anybody have any questions on this first one?
Yes, I did have one question. So
Go ahead,
when you
Layla.
say revolve it around the edge,
Mm-hmm.
that becomes the, like I see you, they're butting up against each other. When I had done it, I had left a bit of space, but because I was thinking about last time. But when you're saying whatever it revolves around is whatever it's going to touch.
Yeah, well, it does not have to be touching. So for example, I could have said, all right, we're going to revolve around this vertical line.
Mm-hmm.
And yeah, it would have been hollow, but yeah, that either one of those things is totally legal. It just, it depends on what you're asked for your
Okay.
axis of rotation to be.
But the axis of rotation is whatever it says revolve it around.
Yeah.
Okay, thank you.
Yep. No problem. All right, let's look at this next one. Let's go purple this time. So again, I'm using this top edge now as my axis rotation. So again, the first thing I'll do, I just want to reflect it. It's already not a straight line, but that's fine. And we're going to have, again, circles, these circular bases on the other side here. That kind of looks like a really short pencil. So hopefully this looks close to what you have. Anybody have any questions about this one? All right, and finally, this is the one we're going to spend the most time on today, is revolving around the bottom edge. So, oh, not good. So for this one, what is my axis of rotation really?
The x-axis?
Yeah, we're just revolving around the x-axis now. So again, I'll recreate this guy. So on the left end, you're going to get a circular base. On this right side, I mean, you're going to get this revolution thing going on, but basically you see on the right-hand side, you kind of have this cone that's missing from the very right end there. So any questions about how I got any one of these 3 solid so far? All right, like I said, we're going to be spending most of our time on this guy here. So we're going to find the volume, the volume of this shape here in 2 different ways. The first way we're going to do is to treat x as the independent variable, and then we'll do this again to find the volume using y as the independent variable. So the first thing we want to do is vary through x. So let's just do this. I'm going to go ahead and recreate this shape one more time. I'm going to try to follow closely. I mean, not exactly. I'm going to show you the way that I usually attack these kinds of problems to set up the volume. So let's draw an elementary, a strip. So this right here, you can say is a delta X interval. Make a thin rectangular strip using that. And I'll just revolve that guy alone around the X-axis. So one thing I want to point out, I mean, you probably already know this, but let's just make it really clear. We're finding volumes here, and basically all we're doing, we're finding the volume of a single shape over and over again and just adding those together. So what is that three-dimensional shape that we're breaking down this solid into? Into many, many what?
Cylinders.
Making this very many cylinders, right? And how do you find the volume of a cylinder?
Pi r squared times h.
Pi times radius squared times height. All right, so this right here, this is always what we're doing to find a volume. When we're using integration to find a volume of a revolution like this, you're always finding the volume of cylinders. We go a little bit further, the rate of change of volume is always going to be equal to some area. And that totally depends on what variable we're using, what's our axis of rotation is. Basically, once you've got those two things figured out, you can figure out what dimension you need to deal with. So we've already said that we're going to vary in the x direction. So basically, as our integral starts, we're going to be accumulating volume by moving our independent variable to the right. So this small strip right here, the small cylinder we made, as x increases, what dimension of our cylinder is changing? Is that going to be the radius or the height? Got one vote for height. Anybody else?
Height as well.
Yep. So I got a second for height. I got more for height. So we're on the right page there. So we agree that we're adding height onto this cylinder. So that tells us what area we need to be dealing with. So if we're adding height to our cylinder, are we adding, basically, if you think of us adding like thin sheets onto the height, basically you're adding to the base. What is the shape of the base? We got one vote for circle. So like I said, the rate of change of volume is always an area. In this case, since we're adding these thin circles, we want to find the area of a circle. So we'll do pi r squared. And just to be really general, I'm going to do like this, pi capital R squared minus pi lowercase r squared. I might have an inner radius and an outer radius. I might only have an outer, but that's fine. We'll just keep it general. So go ahead and get more room on my screen here. Our rate of change is going to come from this quantity here, our rate of change of area, or sorry, our area of any given cylinder. So to help us, basically what we want to do is we want to write an integral, write a function to give us this volume. So to do that, you're going to need to know these four equations here. So, x equals -3, that's the far left side of this. Y equals 0 is the bottom of this trapezoid region here. Y equals 2x is this slanted line starting at the origin, and y equals 2 is the very top edge. So those are our four functions we're going to need to consult to help us find the volume here. So we know the rate of change of volume. So basically what we're trying to do is this. We need to write this rate of change of volume in terms of our independent variable x. So let's start with the outer radius. What is our outer radius for this solid?
Two.
Yeah, Rand says 2. Is that just constantly 2, no matter where I am?
Yes, because y equals 2 for the outer.
Right. So let's just stick with that. Yeah, for this one, yeah, the outer radius, you know, no matter where you are on the x-axis, no matter what your value of x is, your outer radius is going to be 2 units away from the x-axis. So I know that capital R is equal to 2. How about lowercase r? What is our inner radius in this situation?
0.
Okay, I got 1 vote for 0. Anybody else?
It's either y equals 0 or y equals 2x, like depending on where you are.
So, and that's a really valuable insight there. So basically, we're not going to be able to handle this using only one function or one definition of a function here, because on the left-hand side here, we have that the inner radius is 0. Our region we're revolving around the x-axis goes all the way to the x-axis. So we really only have an outer radius. So this right here is basically, you know, we'll call this part 1. This will be part 2. What's the outer radius too? Or what's the outer radius on this right-hand side?
The outer radius is still 2.
Still 2, right? I mean, that's true everywhere. But what is the inner radius? And I'll draw another, you know, strip here just to show.
0 to 2x.
Yeah, so when you say 0 to 2x, remember we can't really use.
Oh yeah, so 0 to 2.
Not quite. So, and to kind of highlight this, let me draw 2 different strips here. If I draw 2 different strips depending on different x values, pretty clear that the outer radius is not going to change, but the inner radius does. So how would I find this inner radius right here? What is going to give me that number?
With the y coordinate?
That's the y coordinate, right? So we'll call it right now, we'll say r equals y. The only problem with that, I mean, r equals y, that's totally true.
You have 3 y values.
We have 3 y values. So which one is the one that actually makes sense for us? Which one really makes sense for the inner radius of this solid? So we said y equals 2 was this top edge, right?
Y is equal to 2x.
I got to vote for y equals 2x. So let's do it this way. I'll say yes, that is correct. But let's rule out the other ones. Y equals 2 is the top edge of this shape. The top edge has nothing to do with the inner radius. That's all about the outer radius, which we already found. Y equals 0 is, you know, that's where we're revolving this shape around. So y equals 0 on this end is the inner radius, but y equals 0 on this end is really not part of the solid. It's not part of the shape. So that's not going to help us figure out what our inner radius is over here. So in this case, our inner radius really is 2x. Any questions on any of that before we go a little further? I think really once you're when you're trying to find the volume of a solid or revolution, I think the most important part is figuring out the basically building up that rate of change function. So now let's try to. So what kind of function am I going to have to use here? So I had to split this up into 2 different situations. So what is my rate of change function going to look like?
Piecewise?
It's going to be a piecewise function, which is something I don't think that you've done with Mark yet, but that's okay. So let's do this first. Let's figure out what our subintervals of x are going to be. So for part one, the left-hand side of our shape, what x values do I want to have that valid for?
-3 and 0.
Okay, I hear one vote for -3 and 0. Anybody else? Tony says the same. Right, so I mean, these here, right here, these functions that bound this region, yeah, x goes as far left as -3. You go any further left than that, there's really nothing there. So it doesn't really make sense to integrate over there. And then once you get to x equals 0, then you're in a new situation. So we know our next interval is going to start at 0, but where does it end? How do we find our greatest value of x we want to use there?
Where y equals 2 and y equals 2x are the same value, or they intersect, which would be x equals 1.
That's exactly right. So I know that basically our shape ends where those two lines meet. So if I set them equal to each other, I get that x equals 1. So here's basically the skeleton of our piecewise function. Now let's build up the definitions here. So when x is between -3 and 0, what is my rate of change of volume function going to look like?
Is it ry of x equals pi times 2 squared?
So I got one vote for pi times 2 squared. How do we feel about that? Anybody have anything else? Anybody have a comment on this? All right, we'll come back to that. How about the next one? When x is between 0 and 1, what's the rate of change?
Pi of 2 squared minus pi of 2x squared, or pi times 2x.
All right, any comments on either one of these two definitions for our function? Bo agrees. So does Jonathan. I'm going to go ahead and just put one more thing in here just to really make it clear. I mean, just to remind you, I mean, not every function you have will have an inner radius to deal with, but it's always good to look for it. So any questions on our rate of change function so far? I think this is like 80% of the battle when you're dealing with a situation like this. All right, so we have that. We got our rate of change of volume. Now let's write a function for the volume. So what would that function look like? Now I want to actually find the volume, not just the rate of change.
We'd have to do another piecewise function.
Okay. I actually don't think we do.
Oh, the integration only goes to a certain point.
So here's the thing about the integration. So typically, let's just do this. Let's do, let's do this. If I were to find the volume of the left-hand side of this, what would that integral look like? Where would it start, first of all?
-3.
-3. And I want it to be a variable function, so I'll just call it x. And then what would I integrate?
The rate of change function.
The rate of change function. So we called that r sub v. Don't want to call it x again. Now, the way I've written this function, would it work between x equals 0 and x equals 1?
Yeah.
Yeah. So since we defined our rate of change function as a piecewise function, we can do the volume function. Basically, you're integrating over a piecewise function. So there's no reason to split this integral up again, because the thing that it's integrating has already been split up into two different segments. Any questions about either one of these two functions, especially the first one? All right, like I said, we're going to do this two ways. So for the second part, we're still going to revolve this around the x-axis, but now we're going to be using y as our independent variable. So instead of me drawing a vertical rectangular strip, I'm going to do a horizontal one. And just to kind of remind you, so much of this process starts the same way it did, no matter what circumstance you're in. We know the volume of the cylinder is pi r squared h. And that reminds me of one thing I forgot to bring up. So in this last example, we said our rate of change was pi r squared, right? So if we look at our volume function, what part of this function here is dealing with the height? Where does the height come from in the situation?
dt.
dt, that's right. So remember, we said this rate of change is pi r squared. And basically dt is a little small change in the x direction. And we already said that as we make little small changes in the x direction, you're increasing the height by a small amount. So really you are just adding up the volumes of many, many cylinders. So now what we have to do, so here's my small rectangle, horizontal rectangle. If I were to revolve this around the x-axis, basically I'm going to get this hollow cylindrical shell that wraps around the x-axis like that. So axis of rotation is still x. Now I am changing my variable in the y direction. So in this case, our x variable was the height. In this situation, as y increases, what dimension of our cylinder is changing? Is that the radius or the height?
The radius.
Layla says radius. I heard a couple of people on the microphone saying radius, and that's exactly right. So, and this is kind of like the way Mark put it in class yesterday. When you're increasing the radius of a cylinder, essentially what you're doing is you're putting paper towels back on the roll. So you're putting those thin sheets back on that roll. So rate of change of volume is always an area. So area is equal to radius or rate of change of volume. What is the shape of the kinds of areas I'm putting back on now as y increases? So basically I have a cylinder. It really is this face right here that's growing.
Just really small tubes.
Really small tubes, right? But I'm looking for a two-dimensional area. So, I mean, just think about a roll of paper towels or a roll of toilet paper. You know, when you pull off a layer, what shape is that? Basically, if you were going to unwind a cylinder, what shape are you going to make?
Or a rectangle?
Rectangle, yeah. I mean, not necessarily square. But yeah, always a rectangle. So then if we're going to try to figure out this area, we have to know what the length and the width of this rectangle are. So here's a cylinder that has radius r and height h. So what are these length and width here of this rectangle?
Two pi r.
2 pi r is one of the sides. So basically what happens is this. Yeah, as you pull off a layer of a cylinder, how long is that layer? It's equal to the circumference of that circle. So that's where 2 pi r comes from. And I see a couple other, no. Tony's saying never mind, but he shouldn't be because the height really is just the height. So yeah, this area here, this rectangular area is 2 times pi times r times h. So now what we want to do is this. Our rate of change of volume, we want to express that in terms of y. So basically we have to express the radius and the height in terms of y. Let's start with the radius. So let's say this first. If we're dealing with radius, is the radius of this cylinder, is that something I should be looking at vertical or horizontal in this example?
Vertical?
Okay, I heard a couple of votes for vertical, and it is. So like we said over here, we said that y, which is traditionally vertical on a graph, we said that y was going to give us the radius, right? So now I'll go ahead and word it the way that Mark likes to. So we know it's vertical, so we know it involves y somehow. Is radius equal to the y coordinate, or is it equal to some other large variation in y?
A large variation in y.
Okay, so if it's not exactly equal to y, we need to have an expression for it. So how can I express the radius in terms of y? Maybe I'll draw a couple of strips in here to show the differences. So how would I express the radius here in terms of y?
The distance from distance from the axis of rotation.
Right, so in general, that's true. So let's say I'm looking at this rectangle here where I just drew an arrow. How would I get how far away this is from the axis of rotation, which is right here?
Use the formula y equals 2x.
I'm sorry, Dylan, go again. I couldn't quite hear you.
Just use the formula y equals 2x.
So you're saying y equals 2x. But remember, we only really care about y. So in this case, r is just equal to y. So no matter where I am, you know, no matter what y value I have, my radius is just going to be how far away I am from basically y equals 0. So in this case, yeah, r truly is just the y value. I'll go ahead and stop there because I think it sounded like that was kind of confusing. Go ahead and ask me some questions. If this isn't quite landing for you, go ahead and let's talk about why. Go ahead and ask me a question.
So why would it just be y? Like, is y defined for that, or is it just, yeah, that's kind of what I'm asking.
Is y defined?
Yeah.
Is that what you asked? So
Yeah.
remember in this case, our goal is basically this for this one. We want to find the volume. You know, I'm not going to put the lower limit, but basically we're finding our volume as a function of y. But y varies, right? Let's just do another extreme example. Let's say for whatever reason, let's say I do this again, but my axis of rotation is down here at like y equals -7. Then let's say I start integrating from up here at y equals 0. Well, if I revolve my solid around this line way down here, then when y equals 0, my radius is not 0. My radius is actually what?
7.
It would be 7. So radius by definition, like after you've revolved this shape, your two-dimensional shape, around an axis to make a three-dimensional shape, that radius is basically just how far away your interval is, how far away this rectangular strip is from your axis of rotation. So let's make this really explicit. This is going to be, you know, y minus 0. Because my axis of rotation is y equals 0. So I am always, basically I'm always comparing my current height, or no, I shouldn't say height, my current y distance to 0. And I got a question in the chat. So in the situation, r equals y because we're rotating around axis and the center is at 0. That's exactly right, Shannon. So yeah, since our center is at y equals 0, then we really can't just treat y as the radius. They are the same. Anything else before we move on to figuring out the height? All right, Tony has an answer. Let's see if we get there. So for the height, first question I'll ask you is this: is height going to be a horizontal or vertical quantity in this example?
Horizontal.
Going to be horizontal. So it's going to deal with x somehow. So to figure out the height, what we should do is this. We need basically for any like an arbitrary rectangle, an arbitrary strip here, we need to know how far to the right it goes and how far to the left it goes. Start with the left end because I think that's a little simpler to see. What's the left end of all three, or sorry, of both of these rectangular strips that I made? I'll go ahead and put in a third one. What is the left end of all of them?
-3.
-3, right? So basically, you know, like I said, we were comparing to 0 here. Now we're going to be comparing to -3. The right end of all these rectangles. Obviously, they're all in a different place. But how am I figuring out where that place is? So Shannon says x. For now, I'll just put x. So yeah, we have height is equal to x plus 3. So am I good? Can I now go ahead and make the integral based on this?
No.
No. What do I need to do first?
Write x in terms of y.
I need to write x in terms of y. Remember, I'm using y as my independent variable. I have to translate this into y. So we have lots of x values on here, but what x value do I need to be using to translate x in terms of y here? Or put it another way, what is the equation of this line right here, this black slanted line?
2x.
Yeah, so h equals x plus 3, but we also know that y equals 2x. So if we rearrange that, we get x equals y over 2. So now we're good. We have height is equal to y over 2 plus 3. So I'm going to go ahead and write down what our rate or change of volume is in this example. And then I'll pause and take some more questions. So it's going to be 2 times pi times radius times height. Anybody have any questions about that, where this function here came from? Any part of it? All right, so now that we have that, we want to define a function that gives the volume for any y. So first of all, what would the lower limit of this integral be? Tony says 0. What else do we think? We agree with him? Have another thought? Okay, got another agreement for 0. And then Bo is asking which interval. That's a good question. Let's talk about that. Do I need to split this one up into something piecewise? I see a couple head nods. So let me go ahead and go back to this our x example. So remember this one, our rate of change was all about radius. On the left-hand side, the outer radius was 2. The inner radius was 0. On the right-hand side, the outer radius was 2. The inner radius was 2x. So there wasn't a function we could write that would give me the radius for that entire interval between, -3 to 1. That's why I had to use piecewise, because the thing that defines the radius changes somewhere in that interval. But if we go back here, we said the radius is y. Is the radius equal to y for this entire shape?
Yes.
Yes, it is.
Yes.
We also said the height was going to be equal to x plus 3. Is that true for this entire interval?
Yes.
Yes. So, and I'll just put that another way, especially for the height, because I think that's a little harder to see. The left end of our shape is always this vertical line, x equals 3. The right end of this shape is always y equals 2x. Since that's always true for the entire interval, I don't need to break this up into pieces. I can use those functions to do this everywhere. I'm really glad that came up, though. It's a valuable thing it's a valuable difference to point out. All right, so I saw a couple of votes for 0, and yes, that is where we're going to start accumulating volume, is from y equals 0. And just to be complete here, what are we going to integrate here?
The rate of change function, so RV of y.
Like that?
Would we have to change the y to a t?
Yeah. Another thing to be careful of. So, I mean, as you can see, I think coming up with the rate of change function is much more important than the volume function itself is going to be fine as long as you are integrating the correct function. So any more questions before I stop sharing?
I just want to confirm about the test, if that's okay.
Yeah, that's fine.
Like problems like these, are we going to be asked, like, since we've made this, what is V of blank?
So my disclaimer at first is that I don't want to promise you anything. But I think so far, every time you've been asked to find a volume, like to give me a number and not just a function, you've been asked to do it using GC, which you will not have available to you on Friday.
Okay.
So I would definitely focus your kind of your review and your study on basically knowing how to knowing what all you need to do for this process and why you need to do all those things.
Okay.
For example, why am I using the area of a circle instead of a rectangle, or vice versa? Why am I choosing this as my lower limit of integration? Things like that. Rodolfo is looking for more examples. Rand is right. The online textbook, which I hope you have all, if you haven't looked at it much, I hope you at least know where it is and have access to it. There will be a ton of stuff there to look at. As far as what module, I'm not sure off the top of my head, but I think the table of contents is pretty descriptive. Actually, whatever the most recent iMath, if you click on any of the links in there, it'll take you to whatever section this is. I just don't know. I don't remember what chapter is dealing with volumes. All right, so you have a quiz for me, but I have kept you 3 minutes late. So let's do this. I have left the quiz open until 10 o'clock tonight. So should make sure you get it done at some point. But don't worry about doing it right now if you have something else to get to. I will stay in the room if anybody has any questions. Otherwise, you are free to go.